Okay, good morning. We're going to talk about the fundamental theorem of calculus and more of its direct connection to the definite integrals and kind of work on that in today's set of notes. So this is really the kind of continuation of what we had learned with the fundamental theorem of calculus before about how the part one is that the definite integral, the function that's inside of the definite integral, is the derivative of the function that is the antiderivative on the outside. So we kind of had that part one of the fundamental theorem of calculus. So now we're going into a little bit more detail. We're going to use this example of Nadine, who is training for her figure skating competition, and her velocity is going to be given by v of t equal to this negative x squared. I just realized that that's a typo, that we should change that here to be t. And let me make sure that everything is hooked up and going. All right, hold on one moment. I have some technical difficulties. Okay, I had to do a little restart there, but this should be t squared and 6t right there, so that I have the correct variables. So we're talking about our velocity as a function of time. The first thing it says is to describe her velocity over the 5-second interval. So the thing I might talk about first is what her initial velocity is. So v of 0, when we plug that in, is going to be 1. So her initial velocity is equal to 1 meter per second. So she's starting out at the time period going 1 meter per second. We might talk about what her velocity is doing. This is a parabola for our velocity curve, and it has a negative lead coefficient. So it's going to be an upside down parabola. So I know that her velocity is going to be increasing initially at a decreasing rate because of the concave down nature of the parabola. And this rate, when we talk about it, is actually the acceleration because it's the rate of change in velocity. At some point, the velocity will will have a max, and that max will occur when your acceleration is equal to 0. Okay, so that would give us a nice peak of it. And I will finish out with it's going to then velocity is going to decrease still at a decreasing rate, which again, we're talking about the acceleration is decreasing. The acceleration is negative in this part and decreasing, whereas up here, the acceleration is positive because acceleration is the slope of the lines. So that kind of gives us an idea of what's happening for her velocity. Now, the next thing we're going to do is we're going to talk about this integral from 2 to 5 of v of t dt. Excuse me. And so taking a look at this initially go back to our idea of accumulation, that this is going to be the net change, also known as the quote unquote net accumulation of net change of the position function. And if you recall from when we did the position problems earlier, this is a net change of position from t equal to 2 seconds to t equal to 5 seconds. That is exactly our quote unquote displacement from t equals 2 to 5 seconds. So that's kind of the idea of looking at how this is directly related. And it's displacement where we use the position function in order to find that. So the first thing is we're going to look at using the calculator on this. So this will kind of be the first time that we've actually used the calculator. Now I already pre-did the calculator up here for us. So what I did, and what you should notice, let me move my thing over to this side, is that in the y equals right now, what's in y1, I put the velocity function. All right, and then when I'm going to quit and go to the home screen, and let me just clear that out so I can show you what I did for that. So when I'm looking at this, so just like we have the ability to take a derivative on your calculator, you also have the ability to do a definite integral on your calculator. So what we're going to do here, you can go to the Math 9. Okay, so that's option number 1. So Math, and then you see down here at 9. The other option, if you'll remember, let me quit out of this and go up here, is that if I do alpha F2, and then notice that down here, the number 4 choice is function int. And so function int is this definite integral. And so you do see that we have this integration command put up. So we're going to start at 2. We're going to go to 5. And this is also why I put it into Y1. I put my velocity curve in Y1 so I can hit alpha F4 and just grab the y1 function. And then we are taking the integrating with respect to x. And so that would be kind of what we're looking at. And then when we integrate that, we just hit enter, and it will use that velocity curve for us and calculate our net change. All right, so going back into our function that we had over here, and let's just slide down a little bit here. So evaluating the integral using Math 9 or using the alpha FTC, Einstein stop. As we're doing this, that gives us that the definite integral from 2 to 5 of v of t dt is going to be 27 meters. All right, now I'm going to pause this for a moment just so that I can go back and I'm going to enter it into the calculator using what's called the classic mode for those of you who have older calculators so that you can see the syntax. I'm just going to pause it so that I don't waste the time and go back, and then I'll come in and I'll show you. All right, so here it is in the classic mode for those of you with the older calculators. When you grab function int, you won't have the nice little pretty print of the calculator with the integral, but you put your function first. Then you always put the variable that you are integrating with respect to, that's the dx part, so you would just put the x there, and then you put your bounds, lower bound and upper bound, and then that would give you your value. All right, let's go back to the program. All right, so I'm coming back in. I had a little bit of technical difficulty, so I'm going to re-record this section and kind of show you what was going on. It stopped syncing to my other computer, my tablet. So at this point, we were here, and it says give a possible position function, S of t, that could represent her position in meters. And so I'm just going to remind you guys that, taking the antiderivative is fairly straightforward for polynomials. So we essentially just went through and took the antiderivative of v of t. So we added 1 to each of the powers, so that gave me the 3, and then we divided. I added 1 to the power, and then I originally had a 6 there, and 6 divided by 2 is 3. Antiderivative of 1 was x, and then I added this plus c on here. So I'm going to highlight that right there. That technically we don't really know what that plus c is. So that as we are kind of talking about it, in a lot of ways, it doesn't really matter. I don't really need to know where I currently am at this moment. All I'm trying to calculate is this idea of displacement or net change. And so down here in the next thing where it says, given a possible position function, whatever it is that you came up with, which, like I said, we don't know what our initial condition is. So we're going to need to have an initial condition, a point that tells us where we are in order to solve for c, which I don't have right now, so I'm just going to leave it as plus c. So now when I come down here to the displacement, find the change in position from 2 to 5 using your general antiderivative that you came up with. So when I was calculating that, you're doing s of 5 minus s of 2, right? That's how you get your displacement. Notice that I have a plus c on both of these. I plugged in 5 into the position function, and then I plugged 2 into the position function. That it doesn't really matter because the 2 plus c's are going to cancel. And so when we're looking at that, and I don't understand why my page is not syncing. Oh, there we go. All right, so we're obviously having a little bit slower internet here today, but the plus c's are going to cancel. And so it doesn't really matter when we're doing that. So if we come down here to part 5, number 5, how are my answers in 2 and 4 related? 1, they are the same. So the idea is that when we are looking at the kind of algebraic way to calculate a definite integral, instead of using the areas that we were using before, what we want to realize is that our net change in that area, that accumulation of area under the velocity curve, is exactly the same as calculating the displacement using a position function. And then the other key thing that we want to talk about with this is that the position function doesn't have to be set at this point. It can be any antiderivative because the constant of integration is not going to matter for displacement. That when we subtract, the c's are going to cancel out. They're going to go away anyway. So most of the time when we do this and we write down an antiderivative, we usually use c equal to 0 simply because that's nicer. But if you already had an antiderivative where c was not 0, we would simply still use it. We would know that the constants would simply cancel out when we do the subtraction. All right, now let's go to the next part and take a look at, well, what if we do know where we are? Now I'm going to pause this so that if it stops syncing, I can come back to this point. There's my... All right, so coming back in, I apologize, I'm having a few technical difficulties today with the videos syncing. I don't know if there's a lot of people on the internet today, but we're given in this number 6 that at t equal to 2, Nadine is 12 meters from the edge of the rink. So that gave us a point that we can use to get the constant of integration, okay? But when we look at this, the idea from the fundamental theorem of calculus is going to be that where you are, your position at t equal to 5, which is what we're trying to find, is going to equal the position at t equal to 2 plus your net change in position, also known as your displacement, from 2 to 5. So those are going to be kind of the ideas that we're looking at here. Now let's put this in terms of the definite integral. So when we look at that, our position at 5 is going to be s of 5. Our position at 2 is going to be s of 2, plus our net change from 2 to 5 of v of t dt. So that adds in, this is kind of the key idea of the fundamental theorem of calculus. Where I currently am, 5, is going to equal where I was at 2, and then where she ended up with her net change, adding her net change in. So for this problem, where we were at 2 was 12. The net change that we had from, hold on, I'm not syncing again. All right, so we can answer the question that where she was at 2 is 12, plus where her net change from 2 to 5, which was 27. So that would give us that she is 39 meters from the edge at that time. And so that's kind of the main key idea that we have in the fundamental theorem, where my position, my current position, is going to be where I was, like any moment in time that you know. We call it an initial condition, but it's at any point in time where you knew where you were, plus your net change from that time. So notice that kind of as I am looking at this, the number that is inside of that, the position that you know, will always be the starting that you have for your net change. And you'll also notice that as you take a look at, you're trying to figure out where you are, which is the 5, and that matches what you have up there. All right, I'm going to stop this video at this point and come in with a part 2 where we talk about finding the actual position function.